Let us continue our lectures on algorithms for data science. We will now see some algorithms that are used in what we call as the classification problems. I will first start by discussing classification problems again. We have done this before, but I thought I will come back to this for this part of the lectures. And then I will tell you the types of classification problems quickly, and then describe some characteristic that we look for in these classification problems. And then I will teach 3 techniques which could be used in solving classification problems. In general, many of the techniques that are used in classification can also be modified or used for function approximation problems. So, this is something that you should keep in mind. Similarly, techniques used for function approximation problems can also be modified and used for classification problems. Nonetheless, in this series of lectures, we will look at these algorithms and then give them a classification flavor, and that would come through both the way we describe the algorithm and also the case studies that are used with the algorithms. So, let us look at what classification means. So, we have described this before. If I am given data that is labeled to different classes, that is what I start with. Then if I am able to develop an algorithm which will be able to distinguish these classes, and how do we know that this algorithm distinguishes these classes? Whenever a new data point comes, if I send it through my algorithm, and if I originally had k different labels, the algorithm should label the new point into one of the k groups. So, that is typically what is called a classification problem. So, pictorially we represent here, here we say okay, here is a group of data, here is a group of data. Now, if I were to derive a classifier, then a line like this could be a classifier, and remember we have seen this in linear algebra and before. I have 2 half spaces, and I could say this half space is class 1 and this half space is class 2. Now, you notice that while I have data points only in a small region, this classifier has derived an unbounded classification region. You could come up with classifiers which are bounded also, we will discuss that later. But here now, if I get a new point, if I get a point like this, then I would like the classifier to say that this point most likely belongs to the class which is denoted by star points here, and that is what would happen. And similarly, if I have a point here, I would like that to be classified to this class, and so on. Now, we can think of 2 types of problems. The simpler type of classification problem is what is called the binary classification problem. Basically, binary classification problems are where there are 2 classes, yes and no. So, examples are for example, if you have data for a process or an equipment, and then you might want to simply classify this data as belonging to a normal behavior of the equipment or an abnormal behavior of the equipment. So, that is just binary. So, if I get a new data, I want to say from this data if the equipment is working properly or it is not working properly. Another example would be if let us say you get some tissue sample and you characterize that sample through certain means, and then using those characteristics you want to classify this as a cancerous or a non-cancerous sample. So, that is another binary classification example. Now, more complicated version of this problem is what we call as a multi-class classification problem, where I have labels from several different classes. So, here I had just 2, but in a general case in a multi-class problem I might have k classes. A classic example again going back to the equipment example that we just described, instead of saying if the equipment is just normal or abnormal, if you could actually further resolve this abnormality into several different fault classes, let us say fault 1, fault 2, fault 3, then if you put all of this together, normal, fault 1, fault 2, fault 3, now you have 4 class problem. So, if I have annotated data where the data is labeled as being normal or as being collected when fault F1 occurred, or as having been collected when fault F2 occurs, fault F3 occurs, and so on, then whenever a new data point comes in, we could label it as normal, in which case we do not have to do anything, or if we could label it as one of these fault classes, then we could take appropriate action based on what fault class it belongs to. Now, from a classification viewpoint, the complexity of the problem typically depends on how the data is organized. Now, if the data is organized, let us talk about just binary classification problem, and many of these ideas translate to multi-class classification problems. In a binary classification problem, if the data is organized like it is shown in this picture here, we call this data as linearly separable, where I could use hyperplane to separate this data into 2 sides of the hyperplane or 2 half spaces, and that gives me perfect classification. So, these are types of problems which are called linearly separable problems. So, in cases where you are looking at linearly separable problems, the classification problem then becomes one of identifying the hyperplane that would classify the data. So, these I would call as simpler problems in binary classification. However, I also have a picture on the right hand side. This also turns out to be a binary classification problem. However, if you look at this data and this data both belong to class 1 and this data belongs to class 2. Now, however you try to draw a hyperplane. So, if I were to draw a hyperplane here and then say this is all class 1 and this is class 2, then these points are classified correctly, these points are classified correctly, and these points are poorly classified or misclassified. Now, if I were to come up similarly with a hyperplane like this, you will see similar arguments where these are points that will be poorly classified. So, whatever you do, if you try to come up with something like this, then these are points that would be misclassified. So, there is no way in which I can simply generate a hyperplane that would classify this data into 2 regions. However, this does not mean this is not a solvable problem. It only means that this problem is not linearly separable, or what I have called here as linearly non-separable problems. So, you need to come up with not a hyperplane, but very simply in layman terms curved surfaces. And here for example, if you were able to generate a curve like this, then you could use that as the decision function, and then say on one side of the curve I have data point belonging to class 2, and on the other side I have data points belonging to class 1. So, in general, when we look at classification problems, we look at whether they are linearly separable or not separable. And from a data science viewpoint, this problem right here becomes a lot harder, because when we look at a decision function in a linearly separable problem, we know the functional form, it is a hyperplane, and we are simply going to look for that in the binary classification case. However, when you look at nonlinear decision boundaries, there are many functional forms that you can look at and then see which one works. For example, one could maybe come up with something like this, or one could maybe come up with things where I just do something like this and so on. So, there are many possibilities. Now, which of these possibilities would you use is something that the algorithm by itself has to figure out. So, since there are many possibilities, these become harder problems to solve. So, all of this we described for binary classification problems. Many of these ideas also translate to multi-class problems. For example, if you take let us say I have data from 3 classes like this here. So, these are 3 classes. Now, if I want to separate these 3 classes and then ask myself if I can separate this through linear methods. Now, it is slightly different from the binary classification problem, because we needed only one decision function, and based on one decision function we could say whether a point belongs to class 1 or class 2. In multi-class problems you could come up with more decision functions, and more decision functions would mean more hyperplanes, and then you can use some logic after that to be able to identify a data point as belonging to a particular class. So, when I have something like this here, let us say this is class 1, this is class 2 and this is class 3. What I could possibly do is the following. I could do a hyperplane like this and a hyperplane like this. Now, when I have these 2 hyperplanes, then I have basically 4 combinations that are possible. So, for example, if I take hyperplane 1, hyperplane 2 as the 2 decision functions, then I could generate 4 regions. For example, I could generate plus plus, plus minus, minus plus, minus minus. So, you know that for a particular hyperplane you have 2 half spaces, a positive half space and a negative half space. So, when I have something like this here, then basically what it says is the point is in the positive half space of both hyperplane 1 and hyperplane 2. And when I have a point like this, this says the point is in the positive half space of hyperplane 1 and the negative half space of hyperplane 2. And in this case you would say it is in the negative half space of both the hyperplanes. So, now you see that when we go to multi-class problems, if we were to use more than one hyperplane, then depending on the hyperplanes you get a certain number of possibilities. So, in this case when I use these 2 hyperplanes, I got basically 4 spaces as I show here. So, in this multi-class problem, which is I have 3 classes, if I could have data belonging to one class falling here, data belonging to another class falling here, and let us say the data belonging to the third class falling here, for example, then I could use these 2 hyperplanes and the corresponding decision functions to be able to classify this 3 class problem. So, when we describe multi-class problems, we look at more hyperplanes, and then depending on how we derive these hyperplanes, we could have these classes being separated in terms of half spaces or a combination of half spaces. So, this is another important idea that one should remember when we go to multi-class problems. So, when you solve multi-class problems, you can treat them directly as multi-class problems, or you could solve many binary classification problems and come up with a logic on the other side of these classification results to label the result into one of the multiple classes that you have. So, these give you some basic conceptual ideas on how classification problems are solved, particularly binary classification problems and multi-class classification problems. The key ideas that I said that we want to remember here are whether these problems are linearly separable or linearly non-separable. And in the linearly non-separable problems, there are multiple options. One way to address the multiple options is through a beautiful idea called kernel methods, where this notion of checking several nonlinear surfaces can still be solved under certain conditions on the nonlinear functions that we want to check using simple I am going to call it linear methods, and I will explain this later in the course. So, the idea here is that if you choose certain forms of nonlinear functions which obey certain rules, and those rules typically are called kernel tricks, then you could use whatever we use in terms of hyperplanes, those ideas for solving those class of problems. So, kernel methods are important when we have linearly non-separable problems. Okay, so with this I just wanted to give you a brief idea on the conceptual underpinnings of classification algorithms. The math behind all of this is what we will try to teach, at least some of it is what we will try to teach in this course. And in more advanced machine learning courses, you will see the math behind all of this in much more detail. So, as far as classification is concerned, we are going to start with an algorithm called logistic regression. We will follow that up with KNN classifier. Then we will teach something called k-means clustering. K-means come under what are called clustering techniques. Now, typically you can use these clustering techniques in function approximation or classification problems, and I am going to teach these techniques and use case studies that give a distinct classification flavor to the results that we are going to see using these techniques. So, I will start logistic regression in the next lecture, and I hope to see you then. Thank you.